Welcome to The Explainer. Today, we're going to peel back the curtain on artificial intelligence. We're not just talking about what it does, but how it does it. We're diving deep into the mathematical engine that actually allows a machine to learn. And you'll see it's not magic, it's just, well, really elegant math. So here's the game plan. We'll start with where the whole idea came from, the human brain. Then we'll define the core problem AI is trying to solve. After that, we'll get into the beautiful math behind the solution, watch it happen in real time, and finally, we'll connect all these dots to the tech you use every single day. Okay, let's dive right in. To really get a grip on AI, we have to start with its original inspiration, the incredible, complex network that is the human brain. So on the left, you've got the real deal, a biological neuron. It's the basic building block of our brain. And on the right, that's its digital twin, the artificial neuron. It takes in a bunch of inputs, does a quick calculation, and spits out a single output. This simple little structure is the fundamental Lego brick of an AI's brain. Now, obviously, one of these artificial neurons isn't going to accomplish much on its own. But what happens when we start stacking them, connecting thousands or even millions of them together? Well, then we get an artificial neural network. And this is the structure that gives an AI the power to actually learn and solve some seriously complex problems. So how does a network full of these things actually learn? Well, it all starts with a very simple, very human idea, learning from your mistakes. It has to first figure out how wrong its guesses are. And that's really the central puzzle here, isn't it? We can't just have a machine guessing randomly forever. We need a system, a method that allows it to measure its own mistakes and then, step by step, get better. To do this, we use a really important tool called a loss function. Don't let the name scare you. It's just a formal mathematical way of putting a number on how wrong the network's guess was. Think of it like a penalty score in a game. The higher your score, the bigger your mistake. One of the most common ways to calculate this is with the mean squared error, or MSE. Now, I know it looks like a scary formula, but let's just walk through it real quick. All it's doing is taking the correct answer, that's y, and subtracting the AI's prediction, y hat. It squares that difference to make sure it's a positive number and to make big errors hurt even more. Then it just averages all those squared errors out. The goal of the AI is simple. Make this final MSE number as small as possible. So we know how to measure error. Now for the really cool part. How does the machine actually reduce that error? We're about to look under the hood at the true engine of machine learning. It's a powerful algorithm called gradient descent. This graph is the perfect way to visualize the whole process. Imagine this curve is a giant valley. The higher up you are, the more error or loss your network has. The goal? It's simple. Get to the very bottom of the valley, that lowest point where the error is at its absolute minimum. And here's the critical piece of the puzzle. The network doesn't just magically jump to the bottom of the valley. It learns by taking small, careful steps. With each piece of data, it slightly adjusts its internal knobs and dials, we call these weights and biases, to make sure the next step it takes is downhill, always moving toward that point of lowest possible error. This table shows that process in action perfectly. We start way up at an x value of 5. The algorithm figures out which way is down and takes a step. And you can see that with every single iteration, every step, the value of x gets closer and closer and closer to 0, which is the exact minimum of this particular function. So how does it know which way is downhill? Well, this is where we need a little bit of calculus. It uses a tool called the derivative. What you see here is the derivative of our error function with respect to one of the network's weights. All this formula does is give us the slope of our valley at our current position. It's like a compass that tells the algorithm the direction of the steepest climb. And to go down, you just walk in the exact opposite direction. All right, enough with the theory. Let's watch this all come together. We're going to see how these iterative steps can train a simple model to actually understand data. And here we go. As the algorithm starts running, just keep your eye on that cost on the vertical axis. You can see it just plummeting. With every step, the model is adjusting its weights, and as it does, it gets smarter. Its predictions get more and more accurate, and that error just melts away. And this is the final result. After all those tiny steps downhill, after minimizing the cost, we're left with a model, represented by that blue line, that has actually learned the relationship hidden in the data. It can now make really accurate predictions for new data it's never seen before. Now, I know this might all seem a little abstract, like a problem from a college math class, but I promise you this exact mathematical process is the hidden foundation for technology you interact with constantly, every single day.
Think about natural language processing. The tech that powers chatbots and translation tools. It uses these exact same principles to figure out how to understand and speak human language. And hey, take a look at step 8 on this diagram, iteration and improvements. That's just a friendly way of saying gradient descent, refining the model over and over again.
For example, when a system analyzes a movie review to see if it's positive or negative, it's not magic. It's using a model that was trained, using gradient descent, to classify the emotional feeling of the words you type. And the applications are just everywhere. From customer service chatbots that actually get better at their jobs over time, to financial systems that monitor the stock market, this core learning algorithm is making our world more intelligent and more responsive in thousands of different ways. So if you take one thing away from all this, it should be this. At the very heart of AI's amazing abilities, there is an elegant, surprisingly simple mathematical search for the truth. The act of learning is really just the act of finding the lowest point in a valley of error. And that leaves us with a pretty deep question. If intelligence can be boiled down to a mathematical process, what are the true limits of what we can build?